So, we will start with our second part of the heat transfer, and as we have seen what are the basic rates, basic modes by which heat can get transferred, and the special considerations that are to be included for the case of convective transport process, which can also be divided into free convection, where there is no external agency forcing the fluid to flow over the subject, over the solid object from which heat transfer is taking place, and we have a case of forced convection. So, the fundamental study of heat transfer starts with our identification of the conservation of energy principle. So, for any object we first have to realize, first have to appreciate the conservation of energy principle, and that conservation of energy principle, when expressed in terms of mathematical relations, would give rise to a complete equation describing the energy transport from or to the object and energy generation inside the object if that is relevant, as a result of which the total energy content of this object will change. Energy can also be changed if you have work, if you include the work done to or by the system. So, work done on the system will enhance its energy, and work done by the system will reduce the total energy content of the object. So, all these considerations must be taken into account while writing the conservation equation for any system. So, we are going to start with the simple conservation equation to begin with, where we will at the moment not consider any work effects. So, all our consideration is the tangible form of energy which comes in or out to or of the control volume as a result of conduction or convection. Okay. So, we start with the conservation of energy relation, which simply says that the rate, the dot represents essentially the rate, the time rate. So, rate of energy coming into the system by either convection, conduction, or a combination of both, plus E dot G, where E dot G denotes the generation of energy inside the system. This generation could be due to like ohmic heating, or due to the presence of a nuclear source in the control volume, minus E dot out, where this is the rate of energy which is going out of the control volume as again as a result of conduction and or convection, and the sum total of all these three is E dot stored. So, rate of change of stored energy in the system. So, when we talk about steady state, as a steady state, the E dot st, the rate of energy stored, is going to be equal to 0. That means, there would not be any net storage of energy as a result of these three processes. The temperatures could be a function of space coordinates, that is, temperature could be different at different points in the control volume, but del T, temperature, by del time, that is, the temperature will not be a function of time. So, del T by del time would be equal to 0. However, we understand that T could be a function of the three space coordinates. And if you think of a solid surface and an air in contact with it, and let us assume that the air temperature is T infinity at a point far from the solid edge is T infinity, the inside temperature is T1 at some location, let us say this is at x equals 0, and this is at x equals L, the temperature is T2. So, you would see later on that in absence of any heat generation in the solid, the temperature profile would be linear, but then it would sharply reduce and asymptotically merge with the temperature T infinity, that is the temperature at a point far from it. So, if you consider this region, which is very close to the solid surface in the fluid, where the temperature sharply changes from T2 to that of T infinity far from the plate, and here you see that the temperature asymptotically approaches the free stream temperature. So this, by analogy with our previous discussion, you can clearly see that this essentially establishes the concept of a thermal boundary layer. So same way as in velocity boundary layer, where the velocity increases as we move away from the flat plate and reaches the value equal to the free stream velocity, the same way the temperature changes from that of the solid and it gradually approaches to the bulk temperature or T infinity, that is the temperature at a point far outside of the effect of the solid present in contact with the fluid. So the distance over which this temperature variation takes place will, in a proper way, in a slightly modified way, will be expressed as the extent in which the heat transfer is taking place, because outside of that the temperature does not vary with distance anymore. So no heat transfer, convective or conductive, is taking place in the region where the temperature reaches T infinity. So ultimately we will try to bring in the same concept as that of velocity or hydrodynamic boundary layer in the case of heat transfer as well, in the form of thermal boundary layer. But coming back to the problem that we were discussing about, so if this is my control volume, this expression applies to the control volume. So E dot in, the amount of energy which comes from the left of the figure, plus E dot G, if this is a nuclear fuel element, then some amount of heat would be generated. If it is not, then E dot G would be equal to 0, and E dot out is the energy which goes out to the air surrounding it, as a result of which the net energy content of the control volume may change, and if it does not change, then we have what we have is a steady state situation. So in absence of energy generation, and if it is a steady state system, E dot in must be equal to E dot out. Now what is control surface? The dotted line which I have drawn can be thought of a control surface, which by definition does not have any mass of its own. So if it does not have any mass of its own, then it cannot store any energy and no energy is generated in it. So at the control surface, E dot in must always be equal to E dot out. So this is these are the some of the concepts which we would use in our subsequent analysis. The next part that we are going to do is the heat diffusion equation, which I am sure you have done before, but very quickly it tells me that if I have a control volume of size dx, dy and dz, and if we consider only conduction, let us say Qx is the amount of heat coming in, Qx is the flux of heat which is coming through the surface through the x phase, and Qx plus dx is going out, Qz is coming in through the z phase, Qz plus dz is going out of the z phase, Qy is coming in and Qy plus dy is going out, and Qx plus dx, that is, can simply be expressed in the Taylor series expansion the same way we have done before. So this is for Qx plus dx, same way you can write for Qy plus dy and Qz plus dz. So they will simply be, you can simply write it, and if you assume that Q dot is the energy generated by some means, could be nuclear, per unit volume inside this, then the total amount of heat generation in this control volume would simply be equal to del x, del y, del z, and E. So this would be equals E dot G, energy generated, and E dot stored would be equal to rho Cp del T by del time del x, del y, del z. Because if you see this rho times del x, del y, del z, is simply equals to the mass of the control volume. So m Cp del T by del time is the time rate of change of energy stored in the system. So you can see it in any textbook. So when you write this write the balance equation as E dot in minus E dot out plus E dot generated is equal to E dot stored in this, and plug in the values of qx plus del x, qy plus del y, and so on, and you simplify, what you would get is del x of k del t del x plus del y of k del t del y plus del z of k del t del z plus q dot, which is the energy generated per unit volume, is equal to rho Cp del T by del time, which is the energy stored per unit volume. This is the amount of energy, net conductive heat flux into the control volume from the x direction, from the y direction, and from the z direction. So if we assume that it is a constant k case, the thermal conductivity of the system is constant, then k can simply be taken out of it, and what you get is del 2 t pi del x square plus del 2 t pi del y square plus del 2 t by del z square plus q dot by k is 1 by alpha del t by del time, where alpha is simply defined as k by rho Cp. So there is a reason why alpha is expressed in here instead of rho Cp by k. I simply write 1 by alpha because alpha has units of meter square per second. So this is called, the alpha is called the thermal diffusivity of the system. When we will talk about when we spoke about the momentum diffusivity, which was denoted by mu by rho, there the unit of mu by rho, which was the kinematic viscosity, that is also, its unit was also meter square per second. So mu by rho is sometimes called as the momentum diffusivity. So these two, that the momentum diffusivity or the thermal diffusivity, having the same units as meter square per second, it came from the concept of diffusion coefficient, which we would discuss when we talk about Newton's, when we talk about the mass transfer process, the conductive mass transfer process, which is Fick's first law of diffusion, which connects the amount of diffusive transport of mass is equal to minus dAb, where dAb is the diffusion coefficient of A in B times del Ca del x if it is a one dimensional mass transport process, and this dAb, the mass diffusivity, has units of meter square per second. So by simply rearranging the terms in the form of mu by rho in momentum transfer and k by rho Cp in heat transfer, and dAb, since all of them have the same units as meter square per second, so borrowing the term from mass transfer, mu by rho is called the momentum diffusivity, k by rho Cp is called the thermal diffusivity, and dAb is simply called the diffusivity or mass diffusivity. So that is why the equation of energy is generally expressed not in terms of k, rho or Cp, but the combination variable which is expressed, which is called the thermal diffusivity. So this is the equation what you would get for conductive transport of heat, only for conduction, only conductive transport of heat where the temperature can vary in x, y and z direction, this is the heat generated per unit volume, and this the entire thing is the total amount of energy stored or lost in the control volume per unit volume. So, this is the starting point, and if I write this equation one more time, what we have is del 2 T by del x square plus del 2 T by del y square plus del 2 T by del z square plus q dot by k is 1 by alpha del time by del t. So, if it's a steady state, then del temperature by del time would simply be equal to 0, and what you would get is d2t dx square plus del 2t del y square plus del 2t del z square plus q dot by k is equal to 0. If it's 1D conduction in steady state, and let us say the temperature is a function, the heat is only getting transported in the x direction, then what you would get is k times del 2, there is no reason for writing it in partial form, k d2t dx square is equal to 0, or you can simply also write as d dx of k dt dx is 0, or in other words what you can write is, what you can say is del q x double prime by dx is equal to 0, since k dt dx is equal to minus of qx. So, this analysis simply tells me that for one dimensional conduction only case at steady state, k times d2t dx square is equal to 0, which directly follows from the previous equation, and obviously there is no heat generation. So, if there is no heat generation, this would be the form. If you have heat generation in the system, then you are going to have k times d2t dx square plus q dot is equal to 0. And this simply can be written as d dx of k dt dx, which is k dq x double prime. So, this is the heat flux, the double prime denotes the flux. So, dqx dx is equal to 0. So, this these expressions are very common and would give rise to several other simplifying cases. So, this is in Cartesian coordinate system. So, if you write it in cylindrical coordinate systems, and you should be able to see it from your text, you would see that for the cylindrical coordinate system, 1 by r del r of k r del t del r plus 1 by r square There is no new concept involved in this cylindrical coordinate expression. It's only that when you transform from Cartesian coordinate system to cylindrical coordinate system, you express everything in terms of r, phi and z, where r is the radial distance, phi is this direction, and z is the axial direction. So, when you transform the coordinate, the form of the equation gets slightly more complicated, but fundamentally it still remains the same. Similarly, in the case of spherical coordinate systems, in your textbook you would be able to see which form the fundamental equation takes when you transform it from Cartesian coordinate system to the spherical coordinate systems, that means in terms of r, theta and phi. So, depending on which coordinate system you are using, you have to choose your conduction equation. I have derived the equation in Cartesian coordinate systems, but in your text you would see the same equations are given in cylindrical coordinate systems as well as in spherical coordinate systems. In the Cartesian coordinate system, qx double prime, the conductive heat transport in the x direction is equal to minus k times dt dx or del t del x. Qy double prime is equal to minus k times del t del y, and so on. In cylindrical and in spherical coordinates, these expressions, for example qr, that is the flow of heat, the flux of heat in the radial direction, for cylindrical systems, for spherical systems would be slightly different, and new terms would appear in the expression for qr in cylindrical and qr in spherical systems. But fundamentally there is no new concepts involved. It still can be derived from the basic fundamental equation that rate of energy in minus rate of energy out plus rate of energy generated is equal to the rate of energy stored in the control volume. So, the transformation of the coordinate system would slightly modify the expression of qx, qr or q theta, q phi and so on, but there is no fundamental difference. So, one should start with the right equation, cancel the terms which are not relevant, and then apply the boundary conditions, relevant boundary conditions, to obtain what would be the temperature variation, the temperature distribution in a solid, be it a rectangular, a cylindrical or a spherical solid, and to get a complete picture of the temperature profile present in such a case. So, when we talk about boundary conditions which are present in a system experiencing heat transfer, let us see what are the possible boundary conditions that can be there. The first boundary condition is the temperature at a point can be specified. So, you precisely know what is the temperature at a specific point. So, if a solid, let us say, is in contact with a fluid and you know what is the temperature of the solid at the edge at x equal to 0 when it is in contact with the liquid, then the temperature at this point is specified. So, the first condition that you can think, first boundary condition that you should look for while solving the equation is the temperature at any point in the control volume is given, is provided, is known to us. So, the first boundary condition which is relevant in heat transfer is one is surface temperature known. So, let us say this is the x direction and this T surface is known, and over here the temperature may vary as a function of x and t, but we know that at x equal to 0 T x T is simply equal to Ts, which is a constant. The second point can be it is a constant surface heat flux. What is a constant surface heat flux? That means you have a way, a means by creating a condition. Let us say this is the temperature profile where T x T is known, and if I draw a slope to this line, so this is essentially del T by del, if this is the x, del T by del x at x equals 0. So, if you multiply this with minus k del T by del x at x equals 0, which is nothing but the heat flux at this surface. So, it could be such that this value of q dot double prime is provided to you. The meaning of q dot double prime s at this surface provided to you, it could be that you have a resistance heater in here. The resistance heater is providing a certain amount of heat into the solid which is in contact with the liquid. So, at steady state, the amount of heat which is generated, which is supplied by the heater, has to come and has to go out of the surface. So, at this point, which is the junction of the liquid solid liquid interface, the heat flux is a constant, and if this is the profile, then as we understand that you can never have conduction, never have convection without conduction. So, conduction is the means at which heat gets transferred to the first layer of liquid molecules. So, minus k del T del x evaluated at x equal to 0, which is the heat flux lost by the solid to the liquid, this must be equal to the amount of heat which is supplied to the solid. So, minus k del T del x at x equal to 0 is q double prime s, which is another way of saying that the surface heat flux at that point is known to us. So, that is the second boundary condition one you can think of. There is the third type of boundary condition is whereby an artificial means you do not allow any heat to cross a specific interface. So, you have this as the solid and you are going to place a perfect insulation at the side. So, if you place a perfect insulation denoted by this black object, what happens is no heat can cross through this insulation and come out on the other side. So, if you can apply a perfect insulation on one side of it, then going back to what we have said, what we have shown here before, this q s double prime is equal to 0. So, if you have an insulated surface, then your q double prime s is equal to 0. So, I call it as 2a. It is a special case of this. So, this would give rise to del T by del x at x equals 0 is 0. So, if by some means you could insulate a surface perfectly, which is an idealized condition, then no heat can cross this interface, q s double prime is 0. So, therefore, del T del x is equal to 0. So, this is known as insulated surface, or it is an adiabatic surface. The condition for this would simply be equals q s double prime to be 0, del T del x equal to 0. In some cases, I am describing this adiabatic surface in slightly more detail. Is, let us say you have a solid, on two sides of it you have liquids, and some amount of heat is being generated in here uniformly. So, everywhere there is some amount of heat which is generated. I would show you later on, but the profile would look something like this, with the central line passing, let us say this is at x equals 0, this is at x equals L, this is at x equals minus L. So, when you consider this plane which is located at x equal to 0, if you see this region, this is your temperature versus x profile. At this point, T at x equals 0, if you see close to this location, what you would see is dt dx is equal to 0. The nature of the curve tells you that for this special case, when you have a solid and some amount of heat is generated uniformly, and suppose we take, which we would see later on, that the profile would be like an inverted parabola, then the apex of the parabola which is located on x equal to 0 will have a slope equal to 0 at x equals 0. So, the x equals 0 plane, no heat crosses from the left to the right or from the right to the left. So, the x equals 0 plane is known as the adiabatic plane. So, for an adiabatic surface, adiabatic plane, or for an insulated surface, as we have seen before. So, both for an insulated surface and for an adiabatic surface, the boundary condition would be the same, which is del T del x to be equal to 0, or in the case of one dimensional conduction case, dt dx is 0 at this. And the third condition could be that I have a convection surface condition. Where you have a surface which is solid, on this side you have a liquid, let us say, and the profile of temperature is this, where you have T infinity, the temperature over here is T infinity, and the heat transfer coefficient involved is H. So, heat will come from here to here by means of conduction, and from here to out by means of convection. So, what happens at steady state is then minus k del T by del x at x equals 0. This essentially denotes the amount of heat which comes in by conduction from the interior up to this point has to be equal to the heat which goes out of convection, and if I use Newton's law, which would simply be H times T at x equals 0 at any time minus T infinity. So, the convective heat loss must be equal to the conductive heat which is coming to the interface. So, by conduction you have some amount of heat coming in, and by convection the same amount of heat is going out. So, this T0 T denotes the temperature of the interface at any given time at location 0, and T infinity is the constant temperature of the bulk fluid situated far from the solid wall. So, this is the convection surface condition. So, we would use the conduction equation to start with in the appropriate coordinate systems with appropriate boundary conditions, and quickly try to solve and see if we can get the temperature profile of a solid object which is experiencing conduction. Initially, we would restrict ourselves to the case of steady state, where the temperature could be a function of x, y, z, or r phi z, or r theta phi, but it is not a function of time. But from our experience, we know that heat temperature can not only change with special coordinates, it can change with time as well. When you let an object, hot object, in air, it slowly cools. There are specific metallurgical processes in which you try to control the cooling rate to impart special properties in the stream, that in the material that you are preparing, which is called quenching. So, the quenching rates play a very important role in the final property of the solid. So, in all these quenching processes, the temperature is going to be a function of time. So, how temperature varies with time, which is commonly called as the transient problem or transient conduction problem, will also play a very critical role in many processes of industrial importance. So, therefore, we not only would try to solve a few problems, model a few problems of heat transfer at steady state, where the temperature can be a function of both x and y and so on. We would also try to solve problems in which temperature could be a function of time as well. And we would see whether it is possible to make certain special assumptions such that the system can be brought into in such a way that we can club all those resistances present in such a system, and the process, the method of that clubbing or lumping all the resistances into one parameter, or the lumped capacitance model. We will talk that lumped capacitance model as well, and then we will move to convection, and finally to the generalized energy equation, which would be used for all subsequent problems.